Welcome back to MATLAB Programming for Engineers. Up to this point in the course, we've covered all the basic building blocks that you need to construct a pretty complex MATLAB program. And what we're going to focus on for the next few weeks is applying those programming techniques to engineering simulations. And what I mean by a simulation is computing the solution to essentially a differential equation. You've probably learned by now that almost all problems in engineering and physics can be described by differential equations, sometimes ordinary, sometimes partial differential equations. And although you spend a lot of time in your academic coursework learning techniques to solve differential equations, what you'll find is that many real engineering problems just aren't tractable. They can't really be solved in closed form using mathematical techniques. So we have to resort to computer simulations. And to give you a little motivation, let me show you an excerpt from a movie that deals with this very problem.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong. How's that? Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method?
Yes.
Well, that's ancient.
But it works. It works numerically.
That's it.
Let's type it up.
Well, the technique that they discussed in that movie, that was the movie Hidden Figures, if you didn't recognize it, Euler's method, which is exactly the one that we're going to be using in this class. It's a very old technique, not the most accurate one by any means, but it's a very simple one. So it's a good one to start out with when learning the basics of discrete time simulation. So the basic concept is this. You take a differential equation and you turn it into a difference equation. That is, essentially you replace the df dt by delta f over delta t. Now, if you think about it, that's the opposite of what you did in calculus. When you derived the idea of a derivative, you started by thinking in terms of small but finite differences, and then you asked what happens in the limit as delta t goes to 0. Well, now we're taking a step back. We're saying let's not let delta t go to 0. Let's let it be some small but finite time interval, and let's calculate our solution in small chunks. As a first example of applying Euler's method, let's consider what's probably the simplest differential equation that there is, and one you've probably seen before, and that's the equation for radioactive decay. This equation says that the number of nuclei that decay per unit time, dn dt, is proportional to the number of nuclei that haven't decayed yet, n of t. And there's a proportionality constant called the decay constant, usually written as lambda. And the minus sign just says that the number of nuclei is decreasing with time because they're decaying. Now, you probably know that you can solve this equation exactly. It's separable, so it can just be integrated. But we're going to pretend we haven't taken Calculus 1, so we don't know how to do that. So we're going to do a discrete time simulation instead. And the first step will be replace the derivative, dn dt, by the first difference, delta n over delta t, where delta n is the difference between the number of nuclei that remain in two successive time steps. And we usually use a subscript index, let's say k, representing the kth time step. So this says that the number of nuclei remaining at time k plus 1 is equal to the number that there were in the previous time step minus the number that decayed during the time interval delta t. And the basic idea of a discrete time simulation is you just apply this difference equation over and over again as k goes from 1 up to as many time steps as you choose to run, and that gives you an approximation for n of t. So what would the code to implement that in MATLAB look like? Well, there's typically some initialization, setting up some parameters. For example, how many nuclei do I want to start with in my simulation? And we're starting with a rather small number here of 1,000 nuclei. What's the half-life of the isotope that I'm simulating? And here we've put in a half-life of 6 hours, which is applicable to an isotope that's used in nuclear medicine, technetium-99m. If you ever have to have a nuclear imaging test, this is what they inject you with. They do that because it decays fast, so it gets out of your body relatively quickly. Then there might be some other preliminary calculations you might need to do. For example, what I'm calculating here is the time constant, which is just 1 over lambda, which I showed you on the previous slide. And that's equal to the half-life divided by the natural log of 2. Then the next step that you might do, it's not entirely necessary, but you might choose to set up a time grid in advance. Now in this case, I happen to be running for a fixed number of time steps, so I know how many time steps there are going to be, so I can set up the time grid in advance. And I'm doing that using linspace, and I've decided I want to run starting at t equals 0 for 4 half-lives. Because in 4 half-lives, the number of remaining nuclei will decay by a factor of 2 to the 4th power, which is 16. And I chose 1,000 time steps, just so that I have a small enough time step to get an accurate simulation. And I'll show you in a minute what happens if you make your time step too large. Then what I need in my calculation is delta t, the delta t that's shown in this equation over here, which is just the difference between 2 successive times. Now, I've also chosen in this case to initialize my n of k array. Okay, remember, n is the thing that I'm interested in calculating, the number of nuclei versus time. And again, since I'm using a fixed number of time steps, I can initialize that in advance to zeros. And then I apply the initial condition, which is just n at my first time step. And remember, indexing in MATLAB begins with 1, not 0. So this has to be n of 1, not n of 0. But it's equal to my initial condition, the number of nuclei that I'm starting with. And then this loop is essentially the simulation. We just go starting with k equals 1 up to as many time steps as we want to do and apply the difference equation. So this is just the MATLAB implementation of this difference equation. And think about it, you should be able to tell me why we need this minus 1 here. Well, we need a minus 1 here because we've got a plus 1 there, and we don't want to run beyond the end of the array. All right, so I've calculated n at each time step, and now I can do a plot of n versus t. So let's see what happens when we run this. Hit the run button, and we get a plot showing n of t. And you can see it's that expected exponential decay curve. You've undoubtedly seen this more than once in your life. Now, if you look carefully, there are actually 2 lines there, because I thought it would be interesting to overlay with the result of my simulation the exact solution. And that's the benefit of applying your simulation to something you already know the answer to. It validates your simulation method. So down here at the bottom, I'm also plotting on top of my simulated result the exact solution, which is just exponential decay. And you see they're right on top of each other, right? Which means our simulation is very accurate. But what would happen if I use the smaller number of time steps? Let's try 50. All right, so a smaller number of time steps means I'm using a much bigger time interval. Let's see how that works out. And you can see now there's a significant discrepancy between the simulation and the exact result. So the simulation isn't as accurate. All right, so you have to be careful about this. You want to make sure your time step is small enough that it gives you accurate results, but not so small that you're doing excessive computation. Because if this is a really complex simulation, Doing 10 times as many simulation steps as you really need could cause this simulation to take hours to run. All right, so that's the basic idea of discrete time simulation applied to a really simple problem. When we come back, we'll talk about how to apply it to mechanics, which is mainly what we're going to be dealing with in this class.